Hi, welcome to the Bitcoin workshop. My name is Nicole, and over the next 3 hours, I'm going to teach you how to build and deploy Bitcoin from scratch. Well, sort of. In this mini-series, you'll implement the transaction ordering layer of Bitcoin and its key logic layer. In particular, you'll build the UTXO ledger model from scratch. Don't worry if you're new to the Rust programming language, Substrate, or even Bitcoin for that matter, as we'll be stepping through the entire implementation in great detail. As always, we'll be using the Substrate open source blockchain framework. Substrate is built in Rust and compiles to binary instruction format called WebAssembly, or WASM. Now, Substrate already provides a lot of the core components of a blockchain, such as the database layer, the networking layer, and various consensus mechanisms. For this workshop, we'll modify the runtime, which is the logic layer of the blockchain. We'll also configure how transactions are propagated across the network via the transaction queue. In a future tutorial, we'll actually go ahead and modify the consensus engine as well. By default, Substrate gives us proof of stake and proof of authority. In the future, you'll learn how to change this to be proof of work, thus reaching true feature parity with Bitcoin. This tutorial separates into 5 sections. Feel free to skip and come back to things, as it might take a while to compile code. And we're covering a lot of information, so I'll be providing the source code for you to follow along. In the first part, we'll get everything set up. I'll go over exactly how the Bitcoin ledger model works as we start to scaffold these basic building blocks. In the next part, we'll dive deeper into the cryptographic security of our chain and secure against malicious transactions, like people trying to double spend tokens, for example. Then we'll go ahead and write some tests. Yay, testing. In the fourth part, we'll encounter a networking race condition where we'll learn how to configure transaction pooling logic. And it turns out that the solution in Substrate is quite simple to implement. And finally, we'll deploy your blockchain. I'll step you through everything, from setting up your Genesis block to teaching you how to use the various user interface and CLI tooling available to you as you launch your blockchain using Substrate. Let's go ahead and get started. First, you'll need to get the latest versions of Rust and WebAssembly tools. In your terminal, go ahead and run these commands to install the Rust programming language and other dependencies. So, what's in a UTXO transaction? What actually gets created when you create a new transaction to spend a previously unspent output? Well, off the bat, we know what the outputs will look like. They will just be new UTXOs that are created from the previous UTXOs that are now destroyed. What's more interesting to examine is the transaction input itself, which is how a UTXO gets authorized to be spent in the first place. You can think of each new input as a cryptographic proof that does 2 things. One is that it references an existing UTXO, in this case UTXO1, that we want to spend in this transaction. In Bitcoin, this field is called an output, and actually references a transaction hash that contains this UTXO. In our implementation, we're also calling it outpoint, but for us, it'll reference a place in the blockchain state where we're storing this UTXO. We'll talk more about this later. The second thing that each input contains is a signature that's signed by the owner of the corresponding UTXO that we're trying to spend, in this case, Alice. And the signature, of course, is signed by Alice's private key. And this private key has to in turn correspond with Alice's private key. That in storage we've designated, in fact, owns this UTXO we're trying to spend in this transaction. This is how we're able to verify that Alice does indeed own this UTXO that she's trying to spend. But notice, with UTXO, you could also easily spend a second UTXO in your transaction that might even belong to a different owner, like Bob. This is why UTXO ledger models are so cool. You, in fact, don't need bank accounts with passwords. To spend Bob's token, you don't need to log into his bank account. You just need permissioning at the level of each money unit itself. Okay, so what are Alice and Bob actually signing over in this transaction? What actually goes into this field here? They're signing over the encoding of the entire transaction. So at the time when Alice and Bob submits a signature, this script field is actually empty. And it's quite obvious to reason about why, since it's quite impossible otherwise. So Alice and Bob, with their own private keys, would sign over everything that you see in yellow. The output fields, the value fields, the pub key fields for every single unit included in this transaction. And then they would post-inject their signatures into their respective transactions before this entire transaction encoding gets submitted. This step is crucial because it ensures that the transactions are tamper-proof when being sent across the network among various nodes. Alice and Bob can effectively lock in exactly how they want their UTXOs to be spent. So for example, if a malicious node tampers with this pub key, sending money to himself, and he forges Alice's signature here, it's then really easy to tell that this was in fact not Alice's key, and this entire transaction won't be able to be verified with any truthy nodes. In this way, our implementation is exactly similar to Bitcoin's, where this field is also called script or signature script. Okay, at this point, hopefully your downloads are all completed. If not, don't worry, just pause the video here and come back to this when you're done. Now let's flip back to our terminal. And let's check that you have the latest version of the rustup toolchain installer by running rustup-v. You can also check your version of the Rust package manager by running cargo-version. And if all of that looks good, you're going to want to go ahead and clone the starter code that I've made for you. We'll be using this boilerplate project throughout the duration of our workshop. So go ahead and git clone from GitHub, Substrate Developer Hub, this project, which is called UTXO-workshop. Once that's all downloaded, let's go into this project. And it's important that we switch into a branch called the starter code branch. So let's do git fetch from remote origin, starter code, and let's check out starter code to be our working branch. This step is important because the master branch contains the finished project, which you can always refer to. But our starting point for this workshop will be this empty project in the starter code branch that I've created for you. In this branch, I've included some dependencies that we'll be using in this workshop already. You can, however, start with a completely fresh Substrate template, which I've linked for you here. And along the way, I'll make it really clear to you which dependencies you will need, and then you can go ahead and import them yourself. Now let's flip back to the terminal, and let's open up our project with our favorite code editor. It doesn't really matter which one you use. I'll be using Visual Studio Code. Let me walk you through the file structure to get oriented. Like any Rust project, your configuration files, like the manifest, are written in TOML format, with simple key-value pairs inside. This is where you can inspect our current project's key dependencies. Now up here, these are the folders that are actually particular to the Substrate framework. This scripts directory can be extended to house helpful scripts that will help you automate your development process. For now, this init bash script just helps you upgrade your Rust to the latest versions. This node directory contains helpful tools and configurations that allow you to specify things like what you want your Genesis chain defaults to be, your CLI commands, and other environment variables that are important for your blockchain project. More on this later. When you finish your project and you build a release of it, the final format of your deployable blockchain will reside in this build target directory here. And last but not least, this runtime subdirectory houses the blockchain runtime, or really the crux of your business logic. You can create multiple individual modules, you can think of them as libraries if you're new to Rust, in source, which all get integrated into the existing blockchain framework via this file called lib.rs. In particular, notice that I've already created a file called utxo.rs for you. This is most of where we'll be working within, and this file will contain the bulk of our implementation. Our starting point will be the utxo.rs file, so let's go there. You can see what we're actually building in this workshop is a custom package within the greater Substrate project, and our package is called UTXO runtime, which is designated by this cargo.toml file here. Our starting point will be the utxo.rs file, so let's go back there. At this point, let's go ahead and do a quick Rust compiler check in our terminal to make sure that this boilerplate code that we're starting off with is okay. So let's flip back to our terminal and type cargo check -p, which designates the particular package that we want to check, and give it our package name, which is UTXO runtime. Since everything is compiling for the first time, this might take a couple of minutes. What we're expecting here is that if you're using my starter code template, this compiler, once it finishes compiling, is going to warn you with a bunch of unused dependencies, which you can see I've included for you in this project up here. So if you see those warnings, don't worry about it. We'll get to using all of these dependencies shortly. If you're using the template, you should be seeing less warnings, but what you should not be seeing are any errors. While our compiler is running and checking our code, let me walk you through the rest of this file. This line here helps your module inherit a lot of the implementations and default capabilities from the existing Substrate framework. So what we're doing here is we're declaring a custom trait called, confusingly, trait for this new module that we're building, which inherits from an existing default Substrate module called system, which provides a lot of helpful default implementations for you. In particular, this trait inheritance lets us then get access to a special data type called events, which will come in handy later. Next, you'll see 3 Rust macros, which you can always tell because of its special syntax. Declare storage is the name of the macro, which is always followed by an exclamation mark, which is then followed by some code scope that the macro implements. If you're new to Rust, just know that Rust macros are code that writes or expands other code. In this case, the code written in here. You can think of declare storage, declare module, and declare events, the 3 macros, as our main developer interface whenever we're working with Substrate. And the code that we write within the scope of each of these macros will be automatically expanded into complicated but working blockchain code. Throughout this project, you'll also notice some custom syntax that might not necessarily be Rust specific within these macros. Now specifically, in declare storage, this is where we can define new storage variables that we want to store on our blockchain state. In declare module, we can define external functions and internal helper functions that will do the state transitioning on our blockchain. You can think of these as the functions that you want your users to be able to call to, say, spend a UTXO token. In the declare events macro, notice that we're using this previously inherited event type from up here. This macro will let us define any on-chain events we want to emit. So whenever anything happens, we can emit an on-chain event that the nodes and the public and any of our users can listen to. And down here, I've included a basic test setup, as we'll be writing some tests for our UTXO implementation a bit later on. Flipping back to our terminal now, there are a bunch of compiler warnings from unused dependencies, but as promised, no errors. And don't worry if your code is still compiling at this point, just go ahead and let it run. At the same time, let's come back to our utxo.rs file, and finally, we are ready to write some code. At a very basic level, we need to let users send transactions, and we need some way to reference the UTXOs that they're spending. So above the declare storage macro, let's start by creating the data types that are needed to represent this feature. From the first part of our workshop, recall that we need 3 different data types: a way to represent the entire transaction itself, a way to represent a transaction input, and a transaction output. So let's go ahead and do that. Let's start by declaring a transaction input. So pub struct transaction input. And recall it needs the fields outPoint and SIG-script. Pub outPoint and pub SIG-script. Recall, the outPoint is actually a reference to a future UTXO to be spent. And where the SIG-script, the signature script, is some sort of proof that the transaction owner is authorized to spend the referred to UTXO here, and it's also a proof that the entire transaction is untampered. Out of the box, Substrate actually gives us various primitive types that we can use to represent hash types. In particular, we have access to H256, which will work here in terms of representing the outPoint, i.e. where the UTXO is going to be stored. And we also have access to a hash data type called H512. You can look up the definitions of all of these different hash variables in Substrate reference documentation. As we can see, hash 512 is a fixed size, uninterpreted hash type with 64 bytes. In our case, our SIG-script is actually going to be twice the size of bytes as the UTXO reference variable. Next, let's go ahead and declare the transaction output variable. We'll do that by declaring another public struct with the name transaction output, with the values value, which is actually the value associated with this UTXO, and a second field pub key of type H256, which will represent the public key that's associated with this output. The other way to think about it is this is the key of its owner. And lastly, we're ready to declare a transaction variable type. So pub struct transaction, which, if you recall, is a collection of transaction inputs and outputs. In particular, we're going to represent the inputs and outputs as a vector of inputs and outputs. So inside transaction, let's declare our array of inputs, which will actually be a type of a vector which contains all of our transaction inputs. And it will also have a vector of outputs, which will be a vector of transaction outputs. At this point, during our construction of our custom data types, we realize that we want our custom data types to be able to exhibit more complex behavior than just existing. We want them to be able to be encoded, or we want these variables to be able to be enhashed. The Rust compiler actually lets us import basic implementations for certain traits via something called a derive attribute. And the way to do that is by designating the derived attributes right above the declaration of your variables, like so. Separately, Substrate also lets us declare a feature for this Substrate runtime. When a feature called std, or standard, is enabled for the runtime, it just means that custom Substrate libraries, like the ability to serialize and deserialize data types as per blockchain setup requirements, become available to us. You can do that by setting the config attributes up here, like so. Deriving the serialize and deserialize traits that are made available to us by Substrate. The Rust compiler actually lets us import basic implementations for some traits via something called a derive attribute, and the way to access that is by doing this. In particular, we want the ability for these newly declared data types to be able to be compared with other data types. We want it also to be able to be ordered, to be cloned, to be encoded, hashed, as well as to be printed during debugging. So let's go ahead and import those abilities here. Separately, Substrate also lets us declare a feature for the Substrate runtime. In particular, when the std, or standard, feature is enabled for the runtime, we get access to custom Substrate libraries, like the example to derive the special traits serialize and deserialize, like so. Since we've done this for transaction input, let's go ahead and copy over these traits for our other declared data types. At this point, let's ask ourselves, what should actually be stored on-chain? What should we implement here in declare storage? Well, we need to store a collection of these transaction outputs somewhere. So how about a mapping of all of the unspent transaction outputs that are created, where we can designate the key or its address to be some hashed reference to the value, which will be a single transaction output. In declare storage, let's create a persistent state variable called UTXOStore, which will be a map where its key is some hash, AH256, and its value is going to be a transaction output. We're going to wrap this transaction output as an option. If you're unfamiliar with Rust, option is a type of enum that either returns sum with the variable inside, or it returns a enumerator none. It's generally a good practice to encapsulate things in option if the value inside is something that we'll be querying for later. I want to do something a little bit fancier here. This declare storage macro lets you automatically build your blockchain state at the Genesis block. This means whenever you build a blockchain with Substrate, you can very easily seed your chain with existing data before you deploy it. This feature is really nice for testing, or if you want to just own all of the tokens on day one yourself. Specifically, in this case, when deploying our UTXO blockchain, we want to be able to pass in a vector of transaction outputs and let the macro automatically seed the UTXO chain state with a list of these outputs. So the way to do that is through some custom Substrate syntax in declare storage. First, we want to add extra genesis. Now, add extra genesis knows to configure some type of chain state that we pass in, i.e. any input variable that we pass in here. In this case, we want to call it maybe Genesis UTXOs. And this input variable will be a type, which is a vector of transaction outputs. Now, coming back to our UTXO store declaration, we'll write more custom Substrate syntax. I'll go ahead and do that now. Okay, there's a lot going on here, so let's step through it. What's actually happening here is that we're telling declare storage, the macro, that when it's building the UTXO store variable, to build a custom hash map based on a closure here. Now this closure specifies how this hash map will be created from this input configuration, this Genesis UTXO variable that we created down here, which once retrieved here is a vector of transaction outputs. Next, we iterate over this vector of transaction outputs to create the respective keys and variables to go into this hash. In particular, for the key of this map, we take a hash of the transaction output value itself. And we do so using a hashing function called Blake2 which is available to you via Substrate. Now, if you scroll up, you'll see that this is one of the dependencies that we've already imported for you here. I need to do one more thing here, which is designate a hasher of identity. Let me explain this. When you define storage maps in Substrate, as we've done here, you must also specify a hasher like this that you want to use. This is a neat feature where we can ask Substrate to do even more things, like change how these keys are constructed as we're creating new maps. In this case, however, we've already designated how we want the keys of our maps to be constructed here. So we just need to designate the identity type of hasher. As its name might imply, this means that this function doesn't do any additional hashing at all. And instead, we just directly use the starting keys that we're generating here as the final storage key for this storage item. Now we're ready to write the external function that will let your blockchain users spend their UTXOs. So in declare module, let's go ahead and create a public function called spend, which takes in the input variables origin and another variable called transaction of type transaction. Origin is a mandatory input given Substrate's design, but we don't actually use it in this implementation, so let's go ahead and ignore it. In the function signature, we also want our function to return something called a dispatch result. This dispatch result will either be an OK containing really nothing because we don't need this function to return anything back to the user, or this function will error out, in which case this dispatch result will be an object error containing the error message, say if the user's transaction has failed. If you're new to Rust, results are like options, which we talked about before, in that it's a custom enum type that helps you with a lot of error handling. Results could either be an OK, containing a return value inside, or an error, retaining an error message. If there are issues during your transaction execution in the runtime, an error will help your transaction halt, revert any state changes, and of course return a helpful error message back to you. So in this case, we know that we always want to return an OK with an empty object, in this case an empty tuple on the inside, at the end of every function, if this function has executed successfully. You can think of these inner parentheses here just as a nil value. For the function logic, we want to do three things. First, we want to check that the transaction is valid. And error out if it's invalid. Next, if the transaction is valid, we need to update our storage items that we've declared up here, namely the UTXO store, to reflect the state transactions, i.e. the new UTXOs that are created. And third, it would be nice at this point to emit some sort of success event, signaling to everyone that our transaction has succeeded. Now, checking that the transaction is valid is the crux of our Bitcoin implementation. We'll actually go really in depth into this in the next section. So let's actually not worry about this for now. And let's write a to-do here to remind ourselves to come back to it. Let's go ahead and write the code which will update our storage each time a transaction happens, namely deleting the old UTXO that's being spent and creating new UTXOs as a result of this transaction. Assuming that the transaction is valid, let's go ahead and implement changing the storage upon a successful transaction. But rather than writing a bunch of code here, I want us to create a helper function that will help us write successful transactions to state. How do we write helper functions in Substrate? So recall that this entire module that we're building implements this trait called trait up here. In Rust, you can easily extend this trait, which applies to this entire module, and add new functions to it. What's cool is that these functions are later accessible anywhere else you import this trait. So let's add our helper function to our trait instead of crowding the spend function here. And let's do that by extending the trait implementation of this module like so. Right above tests, let's do implement on trait in this module, which implements our trait called capitalized trait. Admittedly, this is a little bit confusing, but bear with me here. And then inside this declaration, we're free to implement any number of helper functions or internal functions that we want. So inside, let's create our first helper function called update storage. So function update storage, which takes in a transaction, which is a reference pointer to the transaction. And it returns dispatch result, much like our spend function. And since we're returning a dispatch result, once this function executes to the end, we want to make sure to return an empty OK enumerator. Now this update storage function will do two things. The first is that we, of course, want to remove the UTXO that's been successfully spent in this function from UTXO store. And the second thing is we want to, of course, create the new UTXOs that's declared in the transaction outputs of this transaction. And we want to save those UTXOs to UTXO store. Let's iterate over the transaction inputs to remove them from storage one by one. So for input in referencing the transaction struct dot inputs, we want to reach into UTXO store and remove this particular out point, which, if you recall, is the key at which this old input UTXO is currently being stored. Now, if you're new to Rust, you might notice some custom syntax here. This bracket and bracket colon colon is called a Rust turbofish. And it's special Rust syntax that lets you specify the concrete type for a generic function, method, struct, or anything else that you want to use. In this case, because we're actually in this scope, we can use this turbofish syntax to reference UTXO, which is a variable that we've declared above in declare storage. So next, we're ready to create the new UTXOs that need to exist in UTXO store. Similar to input, let's iterate over the transaction outputs and create the respective new UTXOs. So for each output in referencing transaction.outputs, which if you recall is a vector of transaction outputs, we want to calculate the hash or the key for how each transaction output will be stored, which will be a Blake 256 hashing of a reference to the output itself. And then reaching into UTXO store, we want to insert this new key value pair into our hash map. Now, if you take a minute and pause and think about this implementation, you'll notice that there's something that's very, very wrong here. It's this line here. We're storing UTXOs in a hash of the output, which is a struct, as you recall, of its value and pub key. So say if we're to spend our UTXO and send someone 2 new UTXOs, each of value 50, and their pub key is the same, notice that only one UTXO that we're sending will get stored, even though this is a completely valid user behavior. This line here introduces a very bad storage collision problem. Another issue that might be a little bit more difficult to realize here is what's known as a replay attack, which is where, say, Alice always spends a UTXO of value 50 every day in a recurring way, and she sends them to Bob at address 0x00. Now, a malicious node can just observe her recurring transactions and realize that the UTXOs she's generating are always the same, thus the input signatures that are spending UTXOs are always the same. And this malicious node can simply copy her UTXO signature to spend these UTXOs. Now, to overcome this hash collision problem and this replay problem, we're going to do something a little bit clever here. So instead of hashing just the output variable, we're going to hash the entire transaction, so no more replay attacks are possible. And to avoid UTXO collisions in the same transaction, we're also going to hash the index of each of these UTXOs that are being created. Let's go ahead and modify this line here to do exactly that. So roughly, we're going to pass in a tuple of the entire transaction and the index of this particular output. So the way to do that here is by referencing the encoding of the transaction, which just serializes this transaction into bytes that are a bit easier to encode, and an index variable. And this hash of function is expecting a reference. So this index variable will just be a mutable variable index of type unsigned integer 64 bytes, which we will simply increment as we reach each of these outputs. So here we want to do index equals index checked add which is a type-safe way to add 1 to the variable index, and this actually returns a result in case there's some sort of an integer overflow here. So this returns a result, which means that if something wrong does happen here, we can designate an error message. In this case, we want the error message to just be output index overflow. And to unwrap this result, which is returned from checked add, we want to use a custom Rust shorthand question mark, which just unwraps it and returns the internal index value, which is now incremented by 1. So now we have a fully secure update storage function. Going back to the spend implementation, we can now invoke this helper function by calling self : update storage, and giving it a reference to the transaction that the user is inputting. Now recall, the update storage function signature also returns a dispatch result, so that this function also has a chance to error out this spend function that the user is calling. So since the return value is also a result type, we also need to unwrap it here. At this point, we can flip back to the terminal and run another cargo check on our implementation to make sure that syntactically our implementation so far doesn't have any errors. Well, that's running, and now that we've implemented a function to help us modify the state during every state transition function, it would be really nice if we can emit some sort of blockchain event at this point. This last declare event macro lets you declare such events to be emitted. Inside declare events, we see the declaration of a public enum type called event. What's expected here is a series of enumerators that each represent different types of events we want our blockchain to be able to emit. Let's create a new enumerator in event called transaction success. You can also pass in a unique variable or various variables into this enumerator that will also get printed alongside this event. In this case, let's pass in transaction so that the transaction details can also be printed alongside this transaction success event. Going back to our spend function, let's emit the event before returning the OK result. To do this, we can use a custom Substrate function called deposit event to trigger such events. Now, this function itself, it comes from, if we scroll up, this systems trait that we implemented or that we inherited from up here. What deposit event does is that it basically writes an event into a particular block's event record. This deposit event function, of course, expects an event enumerator, which we've created here, and specifically the enumerator called transaction success. With an input parameter containing the transaction itself. At this point, let's come back to our Rust compiler, and there are some errors. Let's go ahead and resolve this before moving on to the next step. Okay, so the first error message says we cannot infer type value in this declaration here. That is because we have implemented in transaction output public value field of type value when we never declared what value represents. So what I actually intend to do here is create my own custom Rust data type by aliasing an existing data type, which is a cool thing that you can do in Rust. So the way to do that is I can declare a new pub data type called value that is essentially aliasing the data type unsigned integer 128. And the benefit of this is that designating U128 as type value is a lot easier to implement in the remainder of our implementation than typing this U128 again and again. Okay, in our second error, it looks like we've invoked transaction.inputs here, but the compiler is warning us that this variable doesn't actually exist. And that's probably because inside transaction, I forgot to make outputs plural. So let's go ahead and save those fixes and run our cargo check again. And this time, everything should come back without any errors. Oh, and I spoke too soon. It looks like in declare storage, there's an issue here where I inserted an extra close bracket. And I think there's just one more issue here where there's an extra semicolon. Okay, let's run cargo check again to make sure everything compiles. It looks like declare storage is also missing a closing bracket here. And I'm not sure how this happened, but it looks like the declare event declaration doesn't have the right type of scope. Okay, let's run our Rust compiler again. There's one more issue in declare storage here, where instead of transaction outputs, plural, it should just be its singular form. Okay, let's compile our code again and see what's up. Great, everything finished compiling with the exception of a few warnings for the remaining imports we haven't used. There is one more feature we should plan for at this point. Namely, each time that someone spends a UTXO, there might be some leftover value that's unspent. This really adds up since there could be thousands of these UTXO transactions per block. And some people might forget to deploy all of the value in their inputs. By default, we're relying on a proof-of-stake blockchain which has validators who are working to secure the network. It would actually be really cool to turn these leftover UTXO amounts into a reward that's distributed among the validators, say at the end of every block. Instead of burning these UTXOs, we'll be able to use them to properly incentivize our validators to prioritize certain transactions. If you're familiar with Ethereum, this is going to sound a lot like gas usage. The key difference for what we'll be trying to do here is that in our case, in UTXO, this tip to validators will be voluntary and not a prerequisite. Users don't need gas to send transactions. But meanwhile, they can include a higher reward amount to get their transactions prioritized faster by validators. So let's go ahead and implement that. First, on our chain state, we'll need to keep track of a variable called reward total that resets after the reward gets distributed at the end of every block. So inside declare storage, let's create a new variable called reward total, which will be of type value. In Substrate, you can give the variables that you declare free getter functions using the syntax get and then the name of the value that will be returned. In this case, it will be reward total. So in the future, users can easily query this variable from your blockchain using this get function. With reward value declared, next we need to add the reward from each transaction as they come in to this total reward tracker or counter. Conveniently, we already have this update storage function, so let's do it inside here. We're going to want to pass in some sort of reward that's calculated from the inputs and outputs of this transaction. And again, we can calculate that later as we verify this transaction. So for now, let's just create a default value where we designate a reward variable that's equal to 0 of type value. So stepping into update storage, let's go ahead and calculate the new reward total and update that accordingly to storage. At the very top of the function, let's do let this new total. First, let's make sure to change the function signature to expect a reward of type value. Next, at the very top, let's do let some new total equal reaching into our existing reward total for this block in storage. Let's go ahead and get that variable. And let's add this reward that's being passed in from some single transaction and add that to our existing block reward total. So checked add, adding in this reward. And we want to check for any potential value overflows. And if so, return the error that says reward overflow. Unwrap the result to get new total. And then we want to go ahead and overwrite our reward total with this new total. And finally, we want this total reward value to only be dispersed to validators at the end of every block. It would be quite tedious to disperse the rewards at every transaction, so let's do it at the end of every block. And when dispersing these rewards, we want it to be equally shared among all of the validators for that particular block. Now, in default Substrate, you're going to get a different set of validators for every block, and so this implementation conveniently works for that model. And luckily, Substrate has a custom function that also lets you execute specific logic upon every block's finalization. So to do that, we go back into the declare module macro, and we make use of a function called onFinalize. This is a custom Substrate function that the declare module macro recognizes, so make sure you don't use a different name here. Now, everything inside this function scope will be executed by the runtime at the end of every block, after all of the other custom logic is done running. So inside this onFinalize function, let's retrieve this block set of validators into a vector called auth. And the way to do that is we reach into an existing library called Aura and get their set of authorities, turning it into an iterable, and then mapping over this iterable with a simple closure. And what this closure does is it retrieves the correct variable, which in this case is the public key of that particular validator, and it converts it into the data type, which is a H256 that we're expecting in our implementation. And then at the end, you want to collect whatever is being returned here into a type vector. After this, of course, we're going to want to invoke the disperse reward helper function. Specifically, this collect here maps the return values into H256 types. Okay. At this point, let's go ahead and write an internal helper function that then disperses whatever the reward total is at this point in time to this set of validator public keys that we have retrieved. Let's call this helper function that we're going to make disperse reward. And we're going to want to invoke it here later on, so let's just go ahead and do that. And in disperse reward, we're going to want to pass in a reference to our vector auth. Let's go ahead and implement our helper function. Function disperse reward, which of course takes in a list of authorities or validators. which is actually a reference to a vector of H256 public keys. And this function doesn't need to return anything since it's just writing to state. Now inside this function, we're going to want to do three main things. First, we want to divide the reward fairly and calculate how much each validator is going to get. Secondly, we want to then iterate through the validators and then create a new UTXO using their public key, which designates what their share of the reward will be. And third, we'll need to write their UTXOs to UTXO store. So let's go ahead and first calculate the reward. Let reward equals the reward total. And we're going to go ahead and take that from storage. So this take function here deletes the previous reward total. And then we want to calculate the share value, which is also going to be a variable of type value, which is going to equal reward divided by, and we can use this helper function here called checkDiv. And we want to divide it by the total number of authorities, which we can get through calculating the length of the authorities array that's being passed in, and passing that in as a value. Let's go ahead and check whether or not this is a valid calculation, and if not, return the error message, no authorities. And if all of this works, we're going to unwrap and get the internal value, the share reward value. Now there's an edge case here that the share value is 0. So if that's the case, it's not necessarily invalid. It just means that we can exit out of this function earlier. So if the share value is 0, let's go ahead to save computation on the blockchain and just return out of this dispense reward function. Now notice every time you do division, there might be some remainder value. Let's go ahead and calculate that and then decide what to do with it. So the remainder value will equal reward check sub, so subtracted by the product of the share value, which we just calculated, times again the length of the authorities vector, the total number of authorities. Similarly, we want to do a OK OR, and if there's an issue, return the error message sub underflow and unwrap the returning value. I think a good way to handle this remainder value will be to pass it back into the reward total for the next block. So let's go ahead and do that. Reward total, put, and we want to put in the remainder. Next, let's go ahead and iterate through the authorities and create and write one UTXO containing the share value per authority. So for authority in authorities, let's first construct this new UTXO, which will be a transaction output containing the field's value, which will be equivalent to the share value, and a pub key, which will point to the authority. Next, we want to calculate the key in which this new UTXO will be stored in UTXO store. So let's go ahead and do let hash equals, and we want to take the Blake2256 hash of some input here. Now thinking back to the previous security challenge that we resolved, we know that we don't want to potentially allow for any replay or allow for any security issues. Now, thinking through the previous security challenge that we debugged, similarly here, we want to avoid a hash collision. So a clever way to do that is by passing in a tuple of the UTXO and something that's relatively unique. And notice this disperse reward function is executed at the end of every unique block, so the block number must be unique. For the second value in the tuple, let's just pass in the block number, ensuring that every time we're dispersing rewards that are containing UTXOs with unique hashes. Now, it's unlikely that there will be duplicate validators with the same public key in every block's validator rotation. If so, we have more fundamental consensus problems to deal with here. Okay, so to get the block number, you can go ahead and reach into your system module using a function called block number, and we want to convert it into the type that's expected here. So saturated into type 64. And this should work. And finally, we'll need to save these newly generated UTXOs with their respective hashes into UTXO store. So checking that the UTXO store doesn't already contain something that's exactly the same by checking that it doesn't contain the key, hash, and if that's the case, we can go ahead and save it in UTXO store. Let's insert the hash and the UTXO. At this point, if this has been successful, it's cool to log a success message to the console, since the validators will most likely be monitoring that. So the way to do a print line inside the runtime itself is by calling sp runtime and invoke the print function. So here we want to say transaction reward sent to, and then log the particular hash of the new UTXO that was created. So let's do hash as fixed bytes to convert this hash variable into a printable bytes value, and then converting that bytes value into a reference to a vector of U8s, which is actually printable by this command. And similarly, if there is some sort of hash collision or some error that we haven't foreseen, we want the console to log an error message. So in this case, let's do transaction reward wasted due to a hash collision. And let's flip back to the terminal and do a cargo check. And again, at this point, you should only be getting compiler warnings and 0 errors, like so. And that's the first section. To review everything, so far you've built the foundational components of your Bitcoin blockchain. Namely, your users will be able to own and spend UTXOs and reward validators. In the next section, we'll implement some key logic, including securing your Bitcoin blockchain from any potential malicious attacks.